Welcome to another explainer. Today, we're taking a fascinating zoom in, zoom out journey into the literal building blocks of all matter. We're grabbing these foundational chemistry concepts and bringing them entirely to life. Trust me, by the end of this, you're going to look at the physical world completely differently.
Okay, let's dive right into this. Here's our agenda for today. We'll start inside the atom, meet these subatomic particles, decode atomic and mass numbers, zoom out to understand molecules, and then wrap up with a quick test your knowledge section to lock it all in.
Section 1. Inside the atom. Zooming into the microscopic blueprint. So I want you to imagine zooming infinitely close into whatever is right in front of you. Your desk, a glass of water, literally your own hand. Eventually, you hit this, the atom. Now, an atom isn't just some solid cue ball-like sphere. It's got this incredibly intricate internal structure. Right in the dead center is a super dense hub called the nucleus. And swirling around that nucleus in distinct paths or shells are the electrons. Honestly, it's a lot like a miniature solar system, with the nucleus acting as the sun and the electrons orbiting around it like tiny planets. But here is the truly mind-bending part about how an atom occupies space. That nucleus in the center, it holds practically all of the actual mass of the atom. It is unbelievably heavy and dense. But the vast majority of the atom's volume is literally just empty space, mapped out by those swirling electrons. To put that into perspective for you, if an atom were the size of a massive professional football stadium, the nucleus would be the size of a tiny glass marble just sitting right there on the 50-yard line. Section 2, the subatomic particles, the cast of characters inside the atom. Now, let's look at how cleanly we can categorize these particles. Protons and neutrons are tightly locked together in that central nucleus. The proton brings a positive charge of +1, while the neutron is entirely neutral, 0 charge. And since they're pretty similar in size, they both have a relative mass of 1. But then you have the electron, which hangs out completely outside the nucleus in those shells, carrying a -1 charge. And its relative mass? Well, we actually list it as practically 0. So why 0? Well, to give you a stark sense of the scale here, a single proton is roughly 2,000 times heavier than an electron. 2,000! That's why when chemists are calculating the mass of an atom, they consider the mass of that incredibly tiny electron to be absolutely negligible. For everyday practical math, it's virtually 0. Section 3. Atomic and mass numbers. Reading an atom's unique ID card. You see, every single atom has this mathematical ID card that tells scientists exactly what element they're looking at. The crucial point here is understanding the stark difference between these two numbers. First, you have the atomic number, represented by the letter Z, and that is simply the number of protons. If you know the protons, you know the element, period. But the mass number, represented by A, well, that's all the heavy stuff combined. It's the total sum of the protons plus the neutrons locked inside that nucleus. And because of these straightforward definitions, finding the hidden number of neutrons is basically just a super simple math recipe. You just start with your mass number, which is your total heavy particles. Then, identify your atomic number, just the protons. Step 3, subtract the protons from the total. So mass number minus atomic number equals your number of neutrons. It literally works every single time. Section 4, understanding molecules, zooming out to see atoms combine. Let's move on and see how this all builds up. We've spent this whole time zoomed way in on the solitary atom. But the moment atoms combine, we hit the next step up in the hierarchy of matter, which is the molecule. By definition, a molecule is the smallest particle of an element or a compound that can exist freely in nature. It's exactly what happens when atoms chemically link together. Notice the difference between the two gases here. Over on the left, neon is a monatomic gas, which just means it's perfectly happy floating around as a single loner atom. But look on the right, hydrogen is a diatomic gas. In nature, hydrogen atoms really prefer to travel in pairs, holding hands with one another to form a single hydrogen molecule. So let's rapidly break down these molecule categories. First, molecules of elements stick strictly to their own kind. They only contain one type of atom. Now, these can be monoatomic loners like helium, diatomic pairs like oxygen gas or H2, or even polyatomic groups like ozone, which is O3. Then, on the other hand, we have molecules of compounds. These mix and match different elements. Think of H2O combining hydrogen and oxygen to make water, or CO2 combining carbon and oxygen to make carbon dioxide. Section 5. Test your knowledge.
the interactive explainer finale. Okay, let's get energized and lock in everything we've just covered. Question 1. Which of the following particles are located in the nucleus of an atom? Think back to that very first diagram we looked at today. I'll give you a second. The correct answer is protons and neutrons. Remember our visual blueprint. That heavy center is made of the positive protons and neutral neutrons, while the electrons are busy orbiting way outside in the electron shells. Awesome job if you got that one. Moving smoothly right along to question 2. The sum of the number of protons and neutrons in an atom is known as what? Think back to the atom's mathematical ID card we just talked about. Is it the atomic number or something else? The answer is the mass number. That stark contrast is absolutely crucial. The atomic number tells you who the element is by counting only the protons. But the mass number accounts for all the heavy particles combined, so both the protons and the neutrons. And here is our final multiple choice question for today's explainer. Which of the following is a diatomic molecule? Is it A, O2, B, O3, C, P4, or D, S8? Pay very close attention to those prefixes we covered. The correct answer is A, O2. The simple logic here all comes down to the naming convention. Di means 2, so a diatomic molecule has exactly 2 atoms. O3 has 3, which makes it polyatomic. Excellent work today. As we wrap up this explainer, I really want to leave you with this final, kind of mind-bending thought. We learned today that the nucleus holds the mass, but the vast volume of an atom is defined by the empty space of its electron shells. So, if everything is made of atoms, and atoms are overwhelmingly empty space, what does that actually mean about the physical, solid world around us? What does that mean about you and me? It is such a fascinating paradox of physics and chemistry to just sit and chew on. Keep exploring, keep learning, and we'll see you on the next explainer.